All right. Hey, everybody. Thanks for coming to our talk today. I'm Hayden Blauzvern. This is Eve Martin-Jones, and we work on the Google Open Source Security Team, or GHOST for short. Today, we're going to be talking to you about some of our recent research GHOST conducted into the prevalence and impact of leaked credentials in open source software. The problem of leaked credentials is not a new one. People have been leaking credentials ever since there have been credentials to leak. Because of the longevity of the issue, you might imagine that it's a solved problem. However, according to a Google Cloud Threat Horizons report, leaked credentials are one of the top 5 most common cloud compromise factors. Not only are they more common than you might expect, they are extremely costly, with a report by IBM revealing that compromised credentials account for an average of $4.81 million per breach and rank among the 4 costliest incident types. Attacks involving leaked credentials also take longer to identify than other types of attacks because defenders need to distinguish between legitimate and malicious user activity on the network. So, why are projects and organizations today still being compromised by leaked credentials? Research has identified 2 primary reasons. Firstly, running a modern software system requires developers and organizations to manage lots of credentials. Nowadays, if you're a developer of an application, there's a good chance that it's running on a third-party cloud provider as a cluster of microservices run on Kubernetes, interacting with multiple other systems like databases, pub/sub queues, and blob stores. All of these different pieces and all of the people developing these different pieces need credentials to authenticate with each other. That is, all of the edges in these complex architecture diagrams could have separate credentials. That means you're probably managing hundreds or thousands of different credentials, each of which provides access to some or all of your infrastructure. Secondly, it's easier than ever to accidentally leak your credentials. Especially as open source developers, there are so many ways you might accidentally make your credentials public to the internet. Publishing a credential can occur when pushing to a publicly hosted source code repository like GitHub or GitLab, as shown in this image of a GitHub repo with an AWS key found in its commit history. But it could also look like accidentally bundling a leaked credential into an open source software package or a Docker image. Or maybe it's including an unexpected config file in an AI model repository like Kaggle or Hugging Face. That credentials are so easy to accidentally leak is a real worry because research shows that leaked credentials that appear in open source software may be exploited just minutes after being published. This comes from a blog post by Cybernari, and while we highly recommend reading the whole blog post, it's very, very interesting. The summary is that the author deployed software containing canary tokens to a variety of open source artifact repositories like NPM, GitHub, and Docker, measured how long it took for someone to try and use that credential. The results are pretty alarming. Tokens deployed to NPM, PyPI, and GitHub all had exploitation attempts in just under 3 minutes. Now, there is prior art in secret scanning to mitigate token compromise. Source code repositories, hosts like GitHub, GitLab, and Bitbucket, scan repositories for secrets and alert users when one is found. They also have functionality that can block commits that contain secrets for preventing the leak from ever occurring. GitHub also scans NPM packages for leaked credentials. And while secret scanning source code repositories is enormously valuable and undoubtedly prevents a huge number of compromises due to leaked credentials, there are so many different types of open source artifacts, and source code repositories are not the only ones that can contain leaked secrets. This is what inspired GHOST to create a pipeline for identifying and reporting leaked credentials in a broader variety of open source artifacts, and the results of this effort are what we're going to talk about today. In this session, we're going to first describe a high-level overview of the pipeline used to scan open source software artifacts for leaked credentials. We'll talk a bit about some of our key findings from our scan. We'll give you some useful strategies for mitigating and or preventing credential leaks in your project or organization. And finally, we'll discuss what's next for credential scanning in open source software.
Let's get started by looking at the pipeline that we use to scan open source software for leaked credentials. So our pipeline scans artifacts from a variety of sources, including publicly hosted source code repositories like GitHub and GitLab, a variety of open source software package registries, specifically npm.js, PyPI, NuGet, Maven, and we recently introduced support for Ruby gems, and also public Docker image repositories like Docker Hub. Artifacts are pulled into the pipeline by ingestion backends that are responsible for subscribing to upstream alerts for new artifacts, downloading the artifacts and their relevant metadata, and maintaining the state of the artifacts as they change over time. So for example, things might get deleted from upstream. These are then sent to our extraction backends, which unpack the artifact into its constituent files. For example, a PyPI release will be unarchived, a source code repository will have each blob inspected, and a Docker image will be decomposed into its layers and then further decomposed into each of the files in the layer. Each of these files then gets sent to the scanning backend, which scans for a variety of different credential types. If a match is identified, the backend assembles a report for the reporting backend, which connects to the upstream credential provider to report the leaked credential for remediation. Remediation always includes notifying the user that their credential has been leaked, and the credential provider might also take some action like scheduling the credential for destruction in a few weeks, or in serious situations, or maybe depending on a user's configuration, immediately revoking the credential. Let's take a look at how this pipeline might work in practice, and we'll use a PyPI release as an example. The ingestion backend monitors pypi.org to discover when new releases are published. When we see a new release, the ingestion backend downloads and saves it. And in this case, this is a PyPI wheel file, which is just a zip. So the pipeline unzips it and inspects it to produce an index of each file and directory. And you can imagine that this release might contain a root directory, which has files and a bunch of other directories, and each of those directories has a bunch of files and directories and so on. Each of the files that get unpacked are then sent to be scanned. Now this is a pretty harmless init.py file, and it's not found to contain any leaked credentials. But you can imagine there's another file that does contain a leaked credential. In this case, we've got a hard-coded GCP API key as the default argument to this fetch function. The scan backend will detect this leaked credential and pass it on to the reporting backend, which assembles a report, connects to the credential provider, and reports it. In this imaginary scenario, this is a Google Cloud API key, so it's going to get reported to the Google Cloud Credentials Protection team. They will then take some steps to remediate the leak and secure the key. So that might include revoking it or notifying the user of the compromise. So far, our pipeline has scanned over 6.5 billion files extracted from hundreds of millions of open source artifacts. And this includes not just newly published artifacts, but also scanning a corpus of historical artifacts. We've partnered with GCP, RubyGems, and PyPI to scan for a variety of credentials. Specifically, we scan for GCP API keys, GCP service account keys, or SAKs, RubyGems API keys, and PyPI API keys. And we focus on scanning for keys that are reportable, so that when we find them, we can actually take an action to remediate the situation. For example, we don't just scan for private keys because they don't have an inherent provider who we could report them to. We've recently introduced scanning for some additional GCP credential types, but because we don't have complete results for those, we're going to exclude them from our analysis. Okay, now that you know how the pipeline works, let's talk about some of our key findings from running the pipeline across our corpus of artifacts. Before we begin, I want to mention up top some of the caveats that affect the analysis we're going to talk about. First of all, different credential providers return different levels of details when you report a credential. So that means that not all of this analysis is going to include findings from every credential provider. Secondly, to be as cautious as possible, we don't store a ton of information about the credentials on our end once they've been reported. And that's just to try and avoid amassing a huge database of potentially unrevoked credentials. But it does make some types of analysis a bit harder. And finally, because large chunks of this analysis is based off historical scans, it's kind of biased towards unrevoked credentials. So a credential that was leaked, reported, and remediated in 2018 is not going to show up in our scan. But a credential that was leaked and not remediated in 2018 will appear in our results. And so this skews our results towards historical open source artifacts where leaked credentials haven't been remediated. And you might see how that plays out a bit in the data as we go through. Okay, now that we've got that out of the way, let's have a look at some of our results. So out of those 6.5 billion files we scanned, we found around 20,000 unique valid leaked credentials. The majority of what we uncovered were GCP API keys, which is a bit funny because they're not actually technically credentials, but if they're leaked, they can be used for resource abuse, so it's still bad to leak them. The next largest number of credentials we detected were GCP service account keys. And these are one of the more serious keys to leak because they often have outsized privileges and may grant access to entire organizations or projects on GCP. And then we also found a smaller number of PyPI API keys and RubyGems keys. There are two things I want to highlight to you about this number. First, we're explicitly calling out that these are unique credentials. If you look at the total number of valid credentials we found without deduplicating them, the number is quite a bit higher. So while we only encountered 20,000 unique valid credentials, we found around 300,000 instances of valid credentials. So for example, that might look like the same valid credential being found in both a GitHub repository and an NPM package. And this was actually quite surprising to me because just based on those numbers, it looks like every key is being leaked on average around 15 times. But digging in, we find the culprit pretty easily. It's the GCP API keys. So when a valid GCP API key is leaked, it's leaked to a median of 3 different places. And some of them are being leaked many more times than that. We identified about 40 keys that were leaked to over 1,000 different places. That's obviously quite suspicious. So when we dug in, we found some keys like this one. So this is a valid API key, but it's not a secret. It's a key from GCP that's used to identify a GCP CLI tool during anonymous requests. It shows up in a bunch of Docker images, it shows up in NPM, PyPI, Maven, and NuGet packages, and obviously on GitHub as well. So this explains some of those keys that were really widely leaked, keys that aren't actually secret keys. But it doesn't account for the vast majority of those widely leaked API keys. So the largest culprit for these types of leaks happen in NPM packages. And just to be super clear here, this isn't a package that has leaked credentials, it's just a package with a lot of versions. It's fairly common in NPM for packages to have a relatively high number of versions compared to other ecosystems. And we sometimes see packages with hundreds, thousands, or tens of thousands of versions. There's also the concept of organizations in NPM, and one organization might have tens or hundreds of packages. So sometimes what we'll see is that the same key gets included in every single version of a package and or multiple packages within a single organization. And for some really extreme cases, that means the key is getting reproduced thousands of times or tens of thousands of times. So these two factors, the non-secret keys and keys in packages with many versions, explain why our API key results look like this. If we look at the same chart, but for GCP service account keys, the results are a little bit less unexpected. Most GCP SAKs are only ever leaked once, and no service account key we saw was leaked in more than 4 different places. Okay, we've talked about the uniqueness of leaked credentials, but now let's talk about the other word we used to describe them, which was valid. We're able to categorize the credentials we detect into one of 2 categories. To understand how these categories work, let's talk a bit more about the scanning mechanism. Most, though not all of the credentials we scan for are simple strings that can be matched using a regex. So for example, GCP API keys are the string AIZA followed by a series of 35 characters. And a real key might look something like this. I'm glossing over a few details here, but you can imagine that a simple regex matching those 4 characters and then some characters afterwards is going to turn up a lot of matches, not all of which are going to be actual user credentials. We call these type of matches invalid, and they can occur because we found a match that is just coincidental, for example, a part of a base 64 encoded string unrelated to credentials. They might occur when a user inputs a fake credential as part of testing. We often find placeholder credentials where the software is leaving space for the user to insert their own credentials. Or we find credentials that were once active but aren't currently. And these look just like a valid credential, and they were a valid credential at one point. And there could be a number of reasons they're no longer active. Maybe they've been explicitly revoked, or maybe they had an expiry time that's since passed. So if a credential falls into any of these categories, we say that it's invalid. On the other hand, a valid credential is one that belongs to a real user and is currently active. It's sometimes difficult to distinguish between a valid and an invalid credential. For example, how do you tell just by looking at it if a credential is expired? For that reason, we report all possible credentials and let the upstream providers filter out the invalid ones on their end. So while we found around 300,000 instances of valid credentials, we actually found about 1.4 million possible instances of credentials during our scan. And we can see a breakdown of these by credential type. For example, PyPI API keys and GCP SAKs have a much lower validity rate than the others, which could have a few explanations. As I mentioned before, GCP SAKs are some of the most serious credentials to compromise. So developers have a pretty good incentive not to leak those credentials or to take an action if they do end up getting leaked, like revoking the credential. So we've got a feel for the numbers and types of credentials that we've found. Now let's have a look at the sources of each of these leaked credentials. And we're going to go through this by credential type because it's quite specific to which credential you're talking about. And in this section, we're looking at the number of unique credentials that we found in each source. Let's start with GCP service account keys. The biggest source of leaked service account keys was actually Docker images. And let's take a look at why this might be. In a source code repo and even in an open source package, it's quite a lot clearer to know what is going into the artifact you publish. But because of their composition, what goes into a Docker image is less clear. I'm glossing over many details, but you can think of a Docker image as just an ordered list of file system layers, where each layer represents a diff from the previous layer of the files that were added and deleted. These layers are applied sequentially to produce the final output file system. So for example, say in this first layer we add file A, in the second layer we add file B, and in the third layer we delete file A. When I pull the image and apply those layers, the final file system is only going to include file B, not file A. And so you can probably imagine how this could cause some problems when it comes to leaked credentials. Say we introduced a file called secrets.txt, which has a bunch of credentials in it in the first layer of our image. But then we deleted it later on. The final file system is not going to include that leaked credential. So if we scan just that final file system, we might incorrectly conclude that the image does not contain any leaked credentials. But we know there actually are leaked credentials hidden in that first layer of the image. So instead, when scanning or shipping a Docker image, it's important to individually unpack and scan each layer of the image to check for credentials. That way you're looking at the full set of files that actually get shipped with an image. This isn't a hypothetical concern. For example, CodeCov, which is a tool for unifying and visualizing code coverage data and is installed in a bunch of CI systems. In 2021, they wrote a post-mortem which revealed that their system was targeted by a malicious actor who used an HMAC key discovered in an intermediate layer in a Docker image and was able to compromise every CodeCov user. Hopefully that gives you a better idea why we might be seeing so many leaked credentials appear in Docker images. Let's talk about the other major location of valid leaked GCP SAKs, which is somewhat surprisingly GitHub. Despite existing secret scanning, we did find a few currently valid service account keys in GitHub repositories, which could be down for a few factors. Firstly, while we did find a bunch of keys on GitHub repositories, GitHub is a bit overrepresented in this visualization and in our analysis because out of the 6.5 billion files we scanned, 3 billion of them came from GitHub. So while it might look like more people are leaking stuff on GitHub, actually it's not as big of a difference. It's just kind of based on the size of the data set. But we still do find some valid GCP keys on GitHub, and that could be because GitHub doesn't do historical source code scanning, so an SAK could be published in a repository pre-secret scanning being enabled. Or it could be that the service account key was detected and reported, and the end user decided not to revoke it. Keep this in mind because we also found that the main source of leaked GCP API keys was on GitHub. But given the number of valid credentials we found in general, we suspect that it's a combination of historical API keys, and it seems like people are less likely to revoke an API key that's been leaked. So it's quite likely that many of these API keys have been reported previously, and people just decided not to act on them because they're seen as a less serious threat, which is true. We also see leaks occurring in Docker images and PyPI packages, which are the third and fourth most common sources for compromised API keys. And then for RubyGems tokens, the only place that we found valid RubyGems tokens were in Docker images. While our pipeline did identify a few matches that could have been RubyGems across GitHub repositories and even in a few NPM packages, all of these were either test credentials or inactive credentials that may have been previously reported. That's quite interesting. We haven't actually done a historical scan of all our RubyGems packages yet, though we have been scanning new packages for a month or so. So that probably explains why we don't see any RubyGems packages themselves as a source. We've looked at the common sources of leaked credentials at an ecosystem level. Let's talk about some of the common sources of leaked credentials within artifacts in those ecosystems. And this section is going to be a bit more anecdotal based on our experience building the pipeline and also some experiments that we ran throughout. So these are the files in Docker images, GitHub repositories, and software packages that we most often see credential leaks occur. Let's start off with a really obvious one. We find a bunch of leaked credentials in auth-related files like auth.json, auth.py, GCP auth.json, and it's pretty obvious why leaks might be occurring in these types of files. Second, and this is a bit of a more interesting one, we found quite a few leaked credentials in binaries in Docker images. So nowhere will the credential be included in just like a regular text file or a code file, but we do find them like buried within binaries. We also see credentials leaked in Python bytecode, and there was recently a reasonably high-profile incident involving this type of leak. So maybe this is developers using their auth for testing, accidentally building the credential into a compiled object, deleting the auth from their code, but accidentally including the binary or the bytecode when they upload a Docker image. Third, config files, also a pretty obvious place to leak credentials. Your project might include config for a bunch of different things, like interacting with upstream registries or your CI/CD system. We also see a bunch of credentials in setup or initialization files. And this is an NPM specific one, but we did find a bunch of cases of leaked credentials in the dist, but not the source directory. I'm not a JavaScript developer, so I didn't actually know what those directories were until they started showing up in some of our experiments. So yeah, I believe it's a common pattern for NPM developers to have the raw code in the source directory and then a minified or concatenated version of the code in the dist folder, and that's what gets used in production. But we'll find examples where leaked credentials do not appear in the source directory, but they do appear in the dist directory. I guess our main takeaway from this list is leaked credentials can occur literally anywhere, from those really obvious auth-related files to way less expected places. As a developer or organization, what I'd want to be doing is, number one, making sure I know exactly what files are going into the artifacts that I'm going to make public, and number two, doing some sort of scanning on those files to prevent leaked credentials.
So in our last two sections, we're going to have a quick look at joining some of our information about which packages contain leaked credentials with other information we know about those packages. We kind of guessed, based on our early experiments, that credential leaks don't occur that often in really popular packages. And that's something we've been able to confirm. So packages in the NPM, PyPI, and Maven ecosystems are on average transitively depended on by 50 to 100 other packages. But the majority of packages with valid leaked credentials in all ecosystems have zero dependence. That is, there are no other packages that depend on them. This is pretty intuitive. If you're a package that has hundreds of thousands of dependents, the stakes are a lot higher, and if a credential was accidentally published to a package like that, it's probably going to be spotted and remediated quite quickly. The second thing we wanted to know about package versions that contain leaked credentials is how many of them then go on to be deleted from upstream. One remediating action you might want to take when your credential gets leaked is just to delete the entire version or the release or the package from upstream. Interestingly, this seems to be more of a common practice in PyPI than any other ecosystem. For example, we didn't see any Maven versions that contained leaked credentials being deleted upstream. This can definitely be a good thing to do, but make sure that your remediation plan also includes actually revoking these leaked credentials, because malicious actors could still have gotten to your credentials before you were able to delete the package. So, speaking of remediation plans, now that we understand a bit more about what credential leaks look like in open source, let's look at some of the ways that you as an individual or organization can help mitigate the impact of leaked credentials. So firstly, when issuing new credentials, consider the principle of least privilege. This means that users, applications, and processes have only the minimum access necessary to perform their tasks. And to demonstrate the reasons for considering the principle of least privilege, let's look at the example cloud architecture we showed you at the beginning of this talk. Say there's a service account key for the front end that gets leaked, and the service account has a basic IAM permission, like cloud project owner or editor. Anyone with access to that key then has access to all services and infrastructure in the project. If the key for a front end was restricted to only have the permissions it strictly needed to run, Then if the key gets compromised, an attacker will only have access to a subset of the services and infrastructure, making attacks like data exfiltration and lateral movement more difficult. This might sound like an obvious thing to do, but a Google Cloud Threat Horizons report identified that 67% of keys used in confirmed incidents of customer compromise had the basic IAM roles owner and editor, which grant the service account thousands of unnecessary permissions. So to prevent this from happening, cloud providers often provide tools to evaluate permissions and identify which permissions can be removed. Cloud providers also allow you to create policies within your project so that new credentials will be created with fewer permissions by default. Another mitigation is expiring credentials. When building our pipeline, we found thousands of valid credentials that were published years ago, and if these keys had reasonable expiry times, they would no longer have been valid, even if they were detected or remediated. If applicable, you should also rotate your keys regularly, both to mitigate this risk and to get in the habit of rotating sensitive credentials. This is good practice for if you do have a leak, when you'll need to have a plan for how you'll react and have practiced a disaster recovery playbook. Some cloud platforms allow you to set organizational defaults for the expiry time of a service account key that will get applied to all projects within your organization, so take advantage of all of these features if available. We'd also recommend leveraging logging to audit key usage and identify anomalous behavior. The IBM Cost of a Data Breach report showed that attacks involving compromised credentials took longer to identify than other types of attacks because defenders needed to distinguish between legitimate and malicious user activity on the network, which makes threats harder to identify. Many cloud providers now provide automated tooling to monitor key usage and pre-built queries to identify anomalous behavior. It's also important to perform regular audits of who has access to which credentials and how they're being used. When a leak occurs, you need to have a plan for managing leaked credential reports as part of a disaster recovery plan. And as previously mentioned, it's important to not only have this plan, but also to have gone through this plan and the steps of this as well. We'd recommend the first step is to delete the package from upstream if possible. Our research has shown that many package versions with leaked credentials remain public and upstream. Now, leaving these credentials public is especially problematic if you're not able to immediately revoke these credentials, for example, if that would result in a significant impact to your production environment. We recommend rotating the key as soon as possible and leveraging audit logging to see where that leaked key gets used. Finally, it's also important to assess whether a long-lived credential like a service account key is needed at all. There are many scenarios that don't require these types of credentials to be created and especially exported, and it's worth considering other options like service account impersonation or identity federation. CI/CD platforms like GitHub Actions or GitLab CI provide identities for their CI workflows to authenticate to cloud providers without managing credentials. Similarly, package registries offer trusted publishing workflows. Rather than manage an API key to authenticate to the registry, a developer can configure the registry to trust a CI workflow that both builds and publishes an artifact. So we encourage leveraging these as much as possible. Now, of course, even better than mitigating leaked credentials is just preventing these from occurring in the first place. So if you're an individual or organization that publishes open source software, your workflow probably looks something like this. You as a developer are writing some awesome piece of code or some new software. Then you push it to a public artifact repository like GitHub or PyPI, which makes it available to everyone on the internet. This includes good actors like Ghost trying to raise the alarm in case you've accidentally leaked your credentials, but it also includes malicious actors looking to abuse leaked credentials. And as we saw at the beginning, malicious actors work very fast, so it's a race against time as to who can find the leaked credential first. The only surefire way to prevent leaked credentials from being abused is to prevent the leaks from occurring in the first place. If you're a developer, you should make sure that you are scanning the things you publish before you attempt to publish them. And if you're an organization, you should look into incorporating automatic pre-published scanning into your developer workflows. There are a bunch of different ways you can do this. For example, you can introduce automation into your build systems, such as pre-commit checks, to prevent keys from ever being checked in. Some automated build pipelines like GCP Cloud Build can also create build triggers, and there are also open source projects such as Git Secrets, which use Git hooks. And if you're publishing source code to repositories like GitHub or GitLab, make sure to enable their secret scanning. There are also open source tools like TruffleHog, which you can use to scan your artifacts for leaked credentials. And the OSV Scanner project, which was also created by Ghost, is hoping to launch support for secret scanning sometime soon. So with all of this said, let's have a look at what's next for credential scanning in open source software. In collaboration with several other teams at Google, we've contributed to the release of an open source secret scanning library called Veles. And while it's still in the early stages, we're open to accepting external contributions, so if you have a credential that you'd want to see scanned for, please feel free to open a PR. We also want to expand the types of credentials we detect and report from our pipeline. This 20,000 unique credentials that we identified should absolutely be considered a lower bound on the number of credentials being published in open source software. This is what we found scanning only 4 out of probably hundreds or possibly thousands of credential types that are out there. We've started with GCP, and we've had great experience working with PyPI and RubyGems to onboard scanning for their API keys. We're keen to onboard as many credential providers as possible to help make open source as secure as possible. So if you are a credential provider and are interested in us scanning for and reporting your leaked credentials, please contact us by emailing depsdev@google.com. Also, while we're of course very excited about discovering and reporting a bunch of leaked credentials, we'd like to also demonstrate the potential of the pipeline that we've created for scanning our corpus of open source software. One of the areas that we'd love to expand into is scanning artifacts for things like malware. One of our other goals this year is to work with open source artifact registries to enable pre-published scanning. This is the added layer of protection where the registries will scan artifacts before publishing them to open source and notifying the user and/or blocking the upload if leaked credentials are identified. To help with this, Ghost is working on providing an experimental API for registries to integrate with. So if you're the maintainer of a registry and are interested in integrating with a future secret scanning API, please come talk with us or email us. AI, of course, is also top of mind, and with the number and usage of open source AI models growing exponentially, this is unlocking both new types of credentials for developers to leak and new places for developers to leak credentials. So we'd love to work with model repositories like Kaggle or Hugging Face to scan for their credentials, scan their models for credentials, and onboard credential scanning as part of their developer workflows. Well, this brings us to the end of the talk. We've left a few links here where you can learn more about our projects. Thank you all for coming. Are there any questions?